Good morning, Algebra 2 CP students. Hopefully your morning is going well so far and you're ready to continue talking about the quadratic formula. On Monday, December 6th, you may remember that I introduced the quadratic formula to you, sang you a lovely song on about the quadratic formula that I will most certainly do again. And we went through two examples on how to use the quadratic formula, two examples that both happen to work out to integer solutions. Today, what I would like to do is show you three more examples using the quadratic formula and solving quadratic equations. One of which, the first one, will work out to integers, and the last two maybe will have some square roots and some i's mixed in as well, just like we've seen in the past with completing the square. Very quickly, though, to recap the quadratic formula. Quadratic formula states that if you have a quadratic equation in standard form, meaning that it's written as ax squared plus bx plus c is equal to 0, then you can use your quadratic formula to say x equals negative b, or the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. Now, there is a quadratic formula song. Like I said, I will sing it for you once, only once on video. Or at least, no, I'll do it twice. I'll do it in tomorrow's video too for the other group. But in any case, the song, once you sing it, you can't get it out of your head. It's actually hard to say the quadratic formula without singing it. It goes to the tune of Pop Goes the Weasel. It is oh, wait, hold on. Ready? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's it. That song will get stuck in your head for the rest of your life, and you will never forget the quadratic formula. It seems silly, and it is, but trust me when I tell you, every time in years past there have been students humming the quadratic formula song to themselves when taking an assessment to help them remember it. So just saying, it will work. Trust in the song. Okay, but anyway, let's trust in the quadratic formula for now to solve a couple of examples. All right, we'll start with this first example here of x squared minus 11x minus 60 is equal to 0. If we want to solve this using the quadratic formula. All right, well, if I want to solve this equation using the quadratic formula, what I can do is first make sure that we're in this standard form, which we are in this particular case. That's great. Then I can start by identifying my value for a, which in this case is 1 because there's 1 times x squared there. My value for b, which in this case is negative 11. And my value for c, which in this case is negative 60. We'd be able to then say x should equal the opposite of b, negative b, plus or minus the square root, it's hard to not sing it, of b squared, negative 11 squared, minus 4 times a, which is 1, times c, which is negative 60. All divided by all over 2a, 2 times 1. Okay? Notice how as I was plugging that into the formula, I made sure to be careful with my parentheses and my negatives. I will very much discourage you for now from trying to skip steps in your head. All right, please do not try to skip steps in your head. I feel like that's where a lot of students will make mistakes. I've seen it in the past. Yes, it is true that the opposite of negative 11 is positive 11, but by trying to do that in your head, some students may drop a negative sign. Some students in their head, as silly as it is, may say 2 times 1 is 3 because they'll add them instead and then get confused. Okay, so please just take that extra couple seconds. It's very helpful to write out all those steps with the parentheses and being careful of the negatives as well. All right, going forward, I would say x is equal to the opposite of negative 11 is positive 11 plus or minus the square root of. Negative 11 squared is positive 121 minus this product here of 4 times 1 times negative 60. That's going to be what? Negative 240, I believe. It is negative 240. Very nice. So we get 121 minus negative 240, all divided by 2 times 1, which is 2. So we continue working this out. We're going to get x equals 11 plus or minus the square root of 121 plus 240 is going to be 361 all over 2. Notice that becomes positive because a negative, the opposite of a negative is a positive here, right? And now we can take the square root of 361. I hope it's a perfect square. It's good if it is. We can say the square root of 361 is in fact a perfect square. It's 19. So I'd say that x equals 11 plus or minus 19 over 2. And just like we saw with completing the square, that plus or minus means we can now split into two parts and say, well, x should equal 11 plus 19, all divided by 2, or x could equal 11 minus 19, all divided by 2. So let's do this one first. 11 plus 19 is 30 divided by 2, so we'd say x equals 30 divided by 2, which is 15 for our first solution. And over here, I'd say x equals negative, let's see, 11 minus 19. That's going to be negative 8 over 2, which comes out to be negative 4. And those are our two solutions for that problem. All right, so just a quick little recap. Identified my values for A, B, and C, plugged into the formula carefully. Next step is I did the opposite of negative 11. I multiplied these two things together. I did negative 11 squared, and I worked out what this product was. Keep in mind that we're always going to do the opposite of whatever this product is, 4 times A times C. The opposite of that is positive 240 plus 121 is 361. Square root of that is 19, and then we can split into plus or minus and get our two solutions. All right? So that's great, in my opinion, especially, I mean, it's great anyway, but it's great especially when it works out to be two integer solutions. However, when we get radicals and other stuff thrown in there, it doesn't mean we can't do it. It just means that it may be a little trickier. All right, so let's see, especially this simplification step here. So let's see what we're looking at here for another example. Ready? How about something like this? Let's do 4x squared plus 22x plus 3 is equal to 12x. All right, it's a great example. 4x squared plus 22x plus 3 is equal to 12x. Remember that before we use our quadratic formula, as you saw on this side of the page, we have to have our equation looking like this. It has to be ax squared plus bx plus c is equal to 0. Right now, we are not set equal to 0. Right now, there's terms all over the place. So I need to move that 12x over to the left-hand side in order to start by using the quadratic formula. So I'd subtract 12x. We'd get 4x squared plus 10x plus 3 is equal to 0. Now I'm in my standard form. Now I can use my quadratic formula. Again, I'll write it here for you very quickly. Negative b plus or minus the square root of b squared minus 4ac all over 2a. There we go. We can identify that our value for a is 4. Our value for b is 10. And our value for c is equal to 3. Plug into the formula, I would say x equals negative b, so negative 10, plus or minus the square root of b squared, that's 10 squared, minus 4 times a, which is 4, times c, which is 3, all over 2a. And again, a is 4. Okay. Going forward, let's see what we get. I'll get x equals negative 10 plus or minus, let's see, the square root of 10 squared is 100 minus this product. Let's see what we get. 4 times 4 is 16 times 3 is 48. So over 2 times 4 is 8. So 100 minus 48 is 52. So let's say x equals negative 10 plus or minus the square root of 52 all divided by 8. Well, the square root of 52, if you notice, is not a perfect square. But that doesn't mean that we can't simplify it. And that we can do exactly that because we learned how to simplify radicals. We can say, well, the square root of 52, what's the largest perfect square factor of 52? Well, referring to our handy-dandy calculator, if you don't know off the top of your head, you could divide down the list of perfect squares to figure out, hey, which one is the biggest? Let's do, I don't know, 52 divided by 16. Does that go in evenly? Well, help if the calculator was on. 52 divided by 16 doesn't quite work. Going down the list of perfect squares, maybe 52 divided by 9. Rats, still doesn't work. 52 divided by 4, however, does work. Right? 52 divided by 4 is 13. So I can say that the square root of 52 can split apart to be the square root of 4 times the square root of 13. The square root of 4 is 2, so I get 2 times the square root of 13. So I'm going to replace the square root of 52 with plus or minus 2 rad 13 to get x equals negative 10 plus or minus 2 rad 13, 2 times the square root of 13, all over 8. So notice this value just goes right back in here. Okay? So a little extra step if we don't end up with a perfect square there. But it's something that we've worked with in the past. That was the reason we talked a lot about simplifying radicals in quarter 1, because it shows up in quarter 2, quarter 3, quarter 4. So you are definitely expected to be able to do that. Now we can go ahead and break apart. And if you notice, we're going to be reducing as well. I can say x equals negative 10 plus 2 square root of 13 over 8. And x equals negative 10 minus 2 square root 13 over 8. Here, we can't really simplify this in the sense that we can't combine like terms, but we certainly can reduce these fractions. I have 10, 2, and 8. All of those numbers are divisible by 2. So I can reduce this fraction down to be negative 5 plus 1 times the square root of 13 all over 4. Reducing fractions, right? Same thing over here. Same reduction can occur. I'd say it's negative 5 minus the square root of 13 all over 4. And that's that. All right, that's as simple as you can get these. Can't combine any more like terms, so we're done. And notice, not really possible to get answers like this by factoring, right? That's why we need methods like completing the square and the quadratic formula so that we can actually find the solutions of something like this. All right. Hopefully no questions about that. Hopefully it's making sense and sinking in. I'm getting a new piece of graph paper here because I have one more example to show you today. All right, let's do it. Last one of the day. We'll get, let's do 6x squared plus 4 is equal to negative 6x. Okay, last one. So here's another example where we start by things not being in the proper order. We need to make sure we're in that standard form first. So I'm going to add 6x to move that over to the other side. And if there were more terms out of place, then absolutely you have to shuffle them around as need be. It gives us 6x squared plus 6x plus 4 is equal to 0. I like this problem a lot because it has some repeat values in there. It has a and b are both 6, and c is 4. That number 4 also shows up in the quadratic formula. So it's a great exercise, in my opinion, in making sure that you keep your terms like straight. You plug them in where they're supposed to be plugged in. All right. So we see that in this particular case, a would be equal to 6, b would also be equal to 6, and c would be equal to 4. And we'd be able to use our quadratic formula to say, well, x equals negative b, the opposite of 6, plus or minus the square root of b squared, that's 6 squared, minus 4 times a, which is 6, times c, which is 4, all over 2a. And again, a is 6. Going forward from here, we can say, well, x equals negative 6 plus or minus the square root of 6 squared is 36 minus this product. What do we get? 4 times 6 is 24. 24 times 4 is 96, I believe. All over 2 times 6, which is 12. Did everybody see that? Going forward, we'd say x equals negative 6 plus or minus the square root of 36 minus 96. If you need a handy dandy calculator, that's totally fine. I don't know why I keep shutting off, like coincidentally, right as I reach for it. 36 minus 96, do you notice that? We get negative 60 all over 12. The square root of negative 60. Not a perfect square. But we can certainly break this down by finding the biggest perfect square factor, just like we did before, square root of negative 60. The fact that it's a negative, of course, means that right from the start, I'd have to pop out that I. We can say that this is the square root of negative 1 times the square root of 60. The square root of negative 1 is I. Just to save you some time, the biggest perfect square factor of 60 would be 4 times 15. Though make sure you can come up with that on your own, either by using a calculator, going down the list of perfect squares, or through some other method. Going forward from here, the square root of 4 is 2 times I times the square root of 15, so I get 2I rad 15. And notice 15 is a number that you could break down into something like the square root of 3 times the square root of 5, but neither of those being perfect squares means it doesn't really get us anywhere. So it's best to just leave the square root of 15 alone. Let's put that back into our problem now to say that x can equal negative 6 plus or minus 2I times the square root of 15 all over 12. Everybody sees that, how this 2I square root of 15 just travels back over here and goes right in for our simplified version of the square root of negative 60. And the fact that we get an I, notice there was no panicking, there was no crying. It was just like, oh, the negative square root means I. Okay. Now, we can break these apart, because we have that plus or minus, to say, well, x should equal negative 6 plus 2I square root of 15 over 12, and x should equal negative 6 minus 2I square root of 15 over 12. Lastly, a little reducing to do in both of these. We see that this, and this are all divisible by 2. So just like the last problem, I can reduce this down to be negative 3 plus 1I square root of 15 all over 6. And over here, I could say x equals, same thing, negative 3 minus 1I square root of 15 all over 6. And we can't reduce those anymore. We can't combine like terms, so we are finished. So you can see through the first example, second example, and this example, how not only can the quadratic formula be used to find those integer solutions like factoring can, but can also be used to find those radical solutions like completing the square can, and even some that are even more intense than completing the square. In order to get this type of solution by using completing the square, we'd have to delve into fractions, and it would get kind of messy. The quadratic formula makes it not quite as messy. All right. Couple notes I want to make about this last problem in particular. Number one, notice that up at the top, you could have noticed a greatest common factor going on here, and you could have at the very top, if you so desired, simplified this by dividing everything by 2, making this 3x squared plus 3x plus 2 equals 0. If you plug that into the quadratic formula, you would actually have gotten the same answer in the end, but you wouldn't have had this reducing step in between here. You would have immediately have gotten negative 3 plus or minus I rad 15 over 6, because you did the reducing up here. That's not always the case that can occur, but if you notice a GCF and you want to take out a greatest common factor right at the beginning, then by all means, it'll save you a little bit of reducing at the end. If you don't want to worry about it at the beginning, then hey, don't worry about it. At the end is when you'll have to reduce. All right, so that's one note that I want to make about this. Another note I want to make about this is notice that when you're reducing the fractions with all of these things, and that happened in the previous example as well, we're only looking at this number, and this number, correct, to reduce. We don't change the radical at all. Think of if this were an x, right? We wouldn't start to look for and divide the x by a particular value. We wouldn't change it at all. This just stays as the square root of 15. When we look to see if we can reduce, we check the first term, the coefficient, the second term right here, and the constant. The first term, the constant, the second term, that number right there, and the third term in the denominator, that constant right there. Okay? If those are all divisible by something, yes, we can reduce. If they're not, then no, we can't. As mentioned previously, yes, it is expected that you can simplify these radicals in these quadratic formula problems. We've specifically talked about simplifying radicals in class, so it's definitely something that you're held accountable for. All right, quick recap. First problem, great example of using integers for the quadratic formula. No funny business here. It's just a straightforward solve. I think this is a great example of how the quadratic formula works out one step at a time. Second example, we saw what happens if you get a couple radicals along the way. Nothing too different. We've simplified radicals in the past, so it shouldn't be a panic-inducing moment. And your problem just splits off. Keep in mind that reducing that I just mentioned, checking this number, this number, this number, they do reduce by a factor of 2. Same thing over here. If you notice the reduction happening up here, by the way, you could do that at the start before you split off into the plus and minus, but just to keep it consistent, I usually like to do it after. It's easier, I think, for students to follow along that way because they always see, oh, split, then reduce, versus sometimes you can, sometimes you can't type of approach. But if you're comfortable with it there, then by all means do that. In our last example here, we saw a negative square root show up where we just had an I in the mix, but otherwise, no different. All right, cool. Thank you so much for your attention and focus today. I appreciate that. Please try to practice problems on Google Classroom as well if you have an opportunity. Otherwise, have a fantastic rest of your day, and I will see you when I see you. Take care.